Hello everyone, welcome to Chapter 9, Lesson 2. This is Brianne Pernick for Robert Morris University, Math 0900. In this lesson, we are going to be working on simplifying a radical expression with a radicand that is a perfect square, as well as a radicand that is not a perfect square. Now, what I would like to pose to you is that in our last lesson, we started talking about how when we have perfect squares, we can take that and break it into the number that when multiplied by itself made that radicand, and then that is the answer to that perfect square problem. For example, we know that for the square root of 25, we can break that into 5 times 5. Now, what we're posing here is that we can take that 25 and rewrite that as 5 squared, because 5 times 5 will make 25, and we can write repetitive multiplication using an exponent. So the answer to that problem is just 5. We all learned that in the last lesson, and should be in agreement that the answer to the square root of 25 is 5. If we look at the square root of 9, we can break that into 3 squared, because 3 times 3 makes 9. Those should be equivalent statements. And then the answer to that problem is just 3. For the square root of 36, we can rewrite that as 6 squared. And when we evaluate that square root, we get the answer of 6. When we rewrite this way and evaluate it, the square root is always going to be the answer of that non-negative base. So we can conclude then, because of the way that we have been breaking down these problems, that if we had x squared under our radical, what would you conclude that the answer to that problem would be? And think about the other 3 examples that we looked at. This first example, the answer was 5. The second example, the answer was 3. The third example, the answer was 6. In each of those examples, we had a radicand of 5 squared, a radicand of 3 squared, a radicand of 6 squared. In this case, our radicand is x squared. We should be able to conclude that the answer is just x. We can use this idea to simplify radicals. So let me show you how this can work. Now, what we have done in each of these examples is break the radicand into perfect squares. That is technically what we were doing, and we were heavily relying on the laws of exponents to do so. And the law of exponents that we were primarily using here in that we're going to use, I should say, in these examples, is the law that allows us to raise a power to a power. When we raise a power to a power, it says that we can multiply the powers. Okay, so if we use that backwards, I can take 9 to the 4th power and say, well, my power of 4 could have been achieved by having 9 squared being raised to the 2nd power, because the law of exponents says that if I raise a power to a power, I would have to multiply those powers to have achieved the power of 4. So now what you have is something raised to a power of 2. just like we had in each of those previous examples. So if we allow the square root to cancel that square, which is basically what has happened in each of those other examples, because a square root and a square cancel each other. Where we were left with the 5, we were left with the 3, we were left with the 6, we were left with the x. If we allow that square root and that square to cancel each other, the answer here would be 9 squared. And then you could simply evaluate that. In letter B, this is already in the form of something squared. So you could simply allow your square root and your square to cancel each other, and your answer would be 126. Now, letter C, we would want to think to ourselves, in every example we had something raised to the second power. So what could I do to multiply by 2 to get a 6? Well, 3 times 2 made 6. So let's make this 17 to the third power raised to the second power. You always want to have something raised to the second power. So think about multiplication. What times 2 gave you that number, that exponent underneath that radical? So at this point, you can allow your radical and your square to cancel each other, and we will have 17 cubed as our answer. Now, I will tell you a trick in a minute. Let's make sure that we understand what we were doing here before I teach you a trick. Take a minute and do student practice A, B, and C. We will check our work, and then I'm going to teach you a little bit of a trick here. Okay? Do A, B, and C, check your work, and then I'm going to teach you a little trick. Okay, at this point, everybody should have attempted to do A, B, and C, and we're going to review the answers. In letter A, you should have seen that it's already raised to a power of 2. So you can simply allow the radical and the power to cancel each other out, and your answer is simply 6. In letter B, you want to think, well, what times 2 will make 4? 2 times 2 makes 4. So underneath that radical, we want to have 13 to the second power raised to the second power. We're going to allow the radical and the power of 2 to cancel, and we are left with 13 squared. And letter C, we would think to ourselves, well, what times 2 made 12? 6 times 2 made 12. So we have 18 to the 6th power raised to the second power. We allow the radical and the power of 2 to cancel, and we have 18 to the 6th power. Now, in every single one of these examples, I'd like you to notice that we started, every example here, first of all, we had an even power. That is very useful to notice that we have an even power. Now, we went from a 4 to a 2 to a 1, a 6 to a 3, a 2 to a 1, a 4 to a 2, a 12 to a 6. Do you notice a pattern between what is happening as you are evaluating those square roots from start to finish? I've taught you the work. I've taught you the behind the scenes of what mathematically is happening. But there's a shortcut, okay? When you have an even power underneath a radical, you can simply divide by 2 to evaluate that square root. Okay, so when we have an even power under the radical, you can divide the power by 2 to simplify. That will remove your square root and simplify that power. So let's make sure it worked. In letter A, 4 divided by 2 gave us 9 squared. 2 divided by 2 gave us 1. 6 divided by 2 gave us 3, so we had an answer of 17 cubed. Notice that each time you can remove that radical. 2 divided by 2 gave us 6 to the first. 4 divided by 2 gives us 2, an answer of 13 squared. 12 divided by 2 gives us 6, with an answer of 18 to the 6th power. So I have taught you the math, what is going on behind the scenes, as well as a little shortcut. And hopefully the math that goes on behind the scenes helps you to understand the shortcut as well. If you need some assistance there, let me know and I'll be more than happy, okay, to help you out with that and answer any questions you may have. Now, this exact same concept can be applied to variable expressions. You have a choice here. You can do the long math and show your work, or you can choose to divide by 2. I am okay with either way, okay? It does not matter to me which method you want to do. If you choose to say, what times 2 gave me a 6, and break this into x cubed times 2, and allow your radical and your 2 to cancel, you will see that your answer is x cubed. If you simply said 6 divided by 2 is 3, you will see that your answer is x cubed. Either way is fine with me. Letter B, your answer here will be y to the 12th. I was able to get that so quickly by saying 24 divided by 2 is 12. If you prefer to show your work, you could have said what number times 2 made 24? Well, it would be y to the 12th raised to the 2nd, and then we allow those to cancel. Go ahead and take a minute for me and do letters A and B. Pause the recording, complete the problems, and I will give you the answers in just a moment. Okay, at this point, everybody should have solved the problems. For letter A, you should have y to the 9th. The reason being is that 2 times 9 did give you that 18. And for letter B, you should have x to the 15th. Reason being is that 2 times 15 made 30. So whether you chose to break it down and do the work or just simply divide by 2, that should be the answer that you have. Now, for our next set of examples, it's going to be very important that we quickly review the rule for the multiplication of square roots. Now, this is something that will be covered a little bit later in the course, but I do want to quickly cover it right now as well, okay? And what this rule says is that if we have 2 radicals that are being multiplied, okay, the square root of A times the square root of B, we are permitted to combine those radicals and make it one big radical right here that we would have the square root of a times b. If we look at the converse of that, if we have the radical a times b, we're permitted to split that up. That's very similar to what we did with our division of fractions under a radical when we had the fraction of 1/4 underneath the radical and we split it into a numerator and a denominator. This is very similar to that, okay? So we are permitted to combine them under one radical, and we are also permitted to split apart those factors. Remembering this rule can help us to evaluate some square roots faster mentally than by trying to use a calculator, especially when they contain variables. So let's take a look at letter A. Now, if you guys made that chart that I asked you to make, this problem might be a little bit quicker for you there, because you're going to see 225, and a little bell and whistle should be going off for you, because you're going to say, ooh, 225, that's a number in my chart that she told me to make, and the square root of 225 is 15. So you're going to think to yourself, okay, I better split this up and make 225 times the square root of x squared. We are allowed to do that according to that product rule for square roots. So now we can simply evaluate these two square roots. The square root of 225 is 15. The square root of x squared is x. And then we can put this back together as 15x. Now, some people who are really good at solving these types of problems, they don't need to even split them apart. They can simply look at this and say 225x squared, those are both perfect squares. I can just go ahead and evaluate those. Okay? Now, letter B. This is another example that we should split apart. We're going to make it x to the 6th times the square root of y to the 14th. Since both of those are even powers, we can go ahead and simply divide by 2. So 6 divided by 2 gives us x cubed. 14 divided by 2 gives us y to the 7th. So our answer here is x cubed y to the 7th. X cubed y to the 7th. And then lastly, we have example C. So we're going to want to split this up 3 times. We have the square root of 169 times the square root of x to the 8th times the square root of y to the 10th. So again, if you've made that chart for me, you should have a bell and a whistle going off when you see the square root of 169, because that is a perfect square. So you can simply go ahead and evaluate this, and you should get 13. When we do x, the square root of x to the 8th power, we can simply divide by 2 and get x to the 4th. And when we do y to the 10th, again, we can divide by 2 because that's even, and we get y to the 5th. And there's our final answer for this problem right here. Here are some examples here that I would like you to try on your own. Please pause this recording, complete these 3 problems, and when you are prepared, please go ahead and play the recording again, and we will review the answers together. Okay, everybody, at this point you should have completed examples A, B, and C, and let's review what you did here. I would have split this one up and made it 625 times the square root of y to the 4th. When you evaluate the square root of 625, you will get 25. And then using the little trick that I taught you, since 4 is an even answer, or an even number, you would have 4 divided by 2 and get y squared. Final answer. Letter B, we would want to split this into x to the 16th and the square root of y to the 22nd. Both of these contain even powers, so we can simply divide by 2. So we'll have x to the 8th times y to the 11th. But when you have variables, you do not need to use a multiplication symbol. You can just put them right beside each other. Lastly, for letter C, we're going to split that into the square root of 121 times the square root of x to the 12th times the square root of y to the 6th. So then we're going to evaluate, and we have 11 x to the 6th y cubed. Now, as you're going through these and you get better and better at them, you may not need to separate out these powers. You may get better at them and be able to do this math without separating, and just look at each radical and divide by 2 and evaluate your perfect squares without doing this middle step. And if you get to that point where you can do that, that is fine with me. You can simply evaluate that math mentally in your head and jot down your answer. If you're comfortable doing it that way and you're getting the correct answer, I'm okay with that. Now, let's talk about simplifying a radical whose radicand is not a perfect square. Because there will be times where you are being asked to leave your answer in radical form, which means that you cannot put this into your calculator and get a decimal. You're going to be expected to simplify it and leave it in square root form with a radical. So when that happens, what you want to do is break your numbers up using factors that contain a perfect square. For example, let's look at letter A. We have the number 20. I would look at that and say, ooh, I can break 20 up into 4 times 5. Underneath that radical, I have not changed the value, because if I put it back together, it still equals 20. 4 times 5 makes 20. All I've done at this point is break it into the factors that multiplied together to make 20. Now you might be thinking, well, why couldn't you use 10 and 2, right? The reason that I specifically chose 4 and 5 was because 4 is a perfect square. And when we're working with radicals, it should be logical that you want to have perfect squares so that you can evaluate square roots. So at this point, we can use that multiplication rule and break this up into the square root of 4 times the square root of 5. The square root of 4 is 2. The square root of 5 is going to be an irrational, crazy decimal, and we don't want that right now. So we're simply going to leave our answer in radical form as 2 times the square root of 5. And that is exactly how you would write your answer for this problem. You're just going to simply leave it like that. Most of the time, in a problem where you are asked to leave your answer in radical form, that radical at some point is going to cancel itself out further along in the problem, and you're not even going to need it. That's the purpose of leaving it in radical form. Let's look at example B. Okay, for example B, we want to follow exactly the same steps. We want to focus on finding factors of 50, one of which contain a perfect square. I would break this into 25 and 2, because 25 times 2 makes 50. You do not change the value underneath the radical. You leave it the same. You just break it into the factors that made that number. So then we can use that multiplication rule and separate out those factors and have the square root of 25 times the square root of 2 and evaluate the square root for the factor that's a perfect square. So the square root of 25 is 5 times the square root of 2. Leave your answer in radical form. Let's do example C together, and then you guys can do the practice examples on your own. Now for letter C, I would break this one into 16 times 3. 16 is a perfect square, and when we do 16 times 3, we get right back to 48. So then we have square root 16 times square root 3. We can evaluate, and we get 4 root 3. So at this point, I would like for you guys to go ahead and do student practice A, B, and C. Student practice A, B, and C. Pause the recording and then we'll come back together to check our work. Okay, at this point everybody should have solved these problems, and sometimes the hardest part about doing these is finding the perfect square. For 98, I broke this one into 49 and 2. Square root of 49, square root 2. 49 is the perfect square, so we're going to break that 7 root 2. For 12, we broke this into 4 times 3, so that gives us root 4 times root 3, which gives us an answer of 2 root 3. And then letter C, I broke this one into 25 times 3, and then we have 25 times root 3, and we have an answer of 5 root 3. So again, the hardest part about this, in my opinion, is thinking about and finding that perfect square. Sometimes you just have to go through the list of factors for that number until you find the right one. Okay? Now, this exact same procedure that we just did can be used to simplify problems that contain variables that are not perfect squares. Okay? Now, when we had variables that ended with an even exponent, I told you that you could simply divide that power by 2. What I want you to do here is very, very similar. Okay? We have to rewrite this expression so that one of them contains a perfect square. So what we're going to do here is we're going to take our exponent and we're going to break it into a factor of 1x, and then we'll be left with an even 1. So we're going to take x squared and x. If you think about what we just did, I have an x to the first and an x squared. Underneath that radical, I still have 3 x's. If I put them back together, they make an x cubed. Okay? We're doing exactly the same thing that we just did with our numbers, only it's a little bit more abstract because now we're using variables. So you are always going to break these variables into 1x and then an even, whatever it is, so you're going to do 3 minus 1 gives you 2. If you had 5 x's, you would do 5 minus 1 gives us an x to the 4th. If you had 11 x's, you would do 11 minus 1 gives us x to the 10th. Okay, you always want to have an even number of variables and then a single variable. Now the reason that we're doing that is because we're going to split these up and have x squared and x. We know that this one will cancel. We can divide that by 2 and have x root x, and that is your answer there. Now let's take a look at B. Step 1 here. So we're going to split these up and make it x to the 7th, y to the 9th. Step 2, we need to split these up so that we can create a perfect square variable. So we're going to do exactly what we did here, okay? I want you to do the 7 minus 1 trick. So 7 minus 1 gives us x to the 6th times x to the 1st. For the y's, 9 minus 1 gives us y to the 8th times y to the 1st. Now we can use that trick of dividing by 2 to simplify. So we're just going to split all of these up into their own individual square root, and we can use that power of 2 rule that I taught you of dividing to simplify. So 6 divided by 2 gives me x cubed. This one cannot simplify, so we're just going to bring it down. Y to the 8th will become y to the 4th, and y by itself cannot simplify, so it stays in its square root. And there we are. There's our answer right there. X cubed, root x, y to the 4th, root y. Now, this answer needs to be simplified. Let me take this one step further. Once you evaluate the square root, those numbers that are outside of the square root are going to get multiplied together. So we have x cubed y to the 4th. The roots that are left, you're going to put them back together. So we'll have xy. This is our final answer. My apologies. We need to put that back together and combine it all together. Okay, let's have you guys do student practice A and B and finish that off. Go ahead and pause the recording and then turn it back on to check your work. Okay, at this point you should have completed A and B. Let's check and see what you have done here. So you should have thought to yourself, well, I want to subtract 1 from my 11 and split this into x to the 10th times x. Break it up into 2 different radicals and have x to the 10th, that's an x, my apologies, times the square root of x. Use that division of 2 there and do 10 divided by 2 makes 5. So you're going to have x to the 5th times square root x, and there's your final answer. For letter B, we're going to start by splitting this up and have x to the 5th, y cubed. Next step, subtract 1 and split it up. So we have x to the 4th times x, and then we have y squared times y. We can subtract from the 4 to simplify that. So we can divide by 2 to simplify. So we can go ahead and take care of that right now. 4 divided by 2 gives us 2. So that becomes x squared root x. When we divide by 2 for the y, we will get y to the 1st root y. And then we combine our answers back together, so we get x squared y. Under the radical, you will have x, y, final answer. And our last set of examples for today is just a combination of a little bit of everything that we've done today. So it contains numbers, variables, even powers, odd powers. So let's just take a look at what we've done here. I'm going to walk you through the first two and then have you do the last two on your own. So for letter A, we're going to break this into square root 12 times square root y to the fifth. For square root 12, we want to think to ourselves, well, we need to break this into 4 times 3. For square root y to the fifth, we want to make it y to the fourth times y. And now we're simply going to evaluate. The square root of 4 is 2, and that leaves us with root 3. 4 divided by 2 gives us y squared root y. And then once you evaluate those perfect squares, they get multiplied together. So you have 2y squared, and what's left under the radicals can be combined back together using that multiplication rule. So we have root 3y. And there's our final answer. 2y squared root 3y. Now let's take a look at letter B. We're going to split this up. We have 18 root x cubed root 7, oh, my thing is moving here on me, root 7, no, that is y to the 7th, and then we have root w to the 10th. I apologize that that moved on me. Let me get back to my review screen here. Move my object back up. Give me some room here. Okay, should be back, good to go now. So we're going to break our 18 into 9 times 2. Our x, we want to break into x squared times x. Our y to the 7th, we want to break into y to the 6th times y. And our w, we can just leave as w to the 10th because it's an even power. So now let's take care of evaluating these square roots. For our numericals, we can do the square root of 9 is 3, and that leaves us with root 2. Moved my object again. Every time I touch it, it moves, and I apologize. Okay. I might just write off to the side so that it doesn't mess up for you guys. Okay, I'm gonna scoot over here so that it doesn't screw this up for you guys. Okay, so we have 3 root 2. Now when we do our x's, x squared, divide that power by 2, and you're left with x root x. For the y's, divide that power by 2, and you're left with y cubed root y. And when you take care of your w's, just divide that power by 2, and you get w to the 5th. Anything that you evaluated the perfect square for gets multiplied back together. So we have 3 times x times y cubed times w to the 5th. Anything that is still under a radical gets multiplied together. So we have times root x y. And there's a 2 under a radical as well. My apologies. 2xy underneath that radical. So final answer there. Now I would like for you guys to do student practice A and B on your own. Please take a minute and complete those, and then we will come back together and check our work in just a moment. Okay, at this point everybody should have been able to complete these, and you should now be ready to check your work with me. For letter A, you should have broken 48 into 16 times 3, and we would have wanted to break x to the 11th into x to the 10th times x. And now we're going to evaluate those perfect squares. So the square root of 16 is 4, and that will leave us with root 3. The square root of x to the 10th is x to the 5th, and that leaves us with root x. And now we're going to take our perfect squares that we've already evaluated and multiply them back together. So we have 4x to the 5th, and put our what is left underneath the radicals. We're going to combine our radicands back together and have 3x underneath that radical. And there is our final answer for letter A. And now letter B, we have the square root of 121. That does not need broken up because it's already a perfect square. We have x to the 6th. We have y to the 7th, which we will break into x to the 6th times y. And then we have z to the 8th, and since it's even, we'll leave it be. We are now ready to go ahead and start evaluating those perfect squares. So the square root of 121 is 11. The square root of x to the 6th is x cubed. The square root of y to the 6th is y cubed, and that will leave us with a root y. And the square root of z to the 8th is z to the 4th. We take all of the perfect squares that we evaluated and combine them back together on the outside. So we have 11 times x cubed times y cubed times z to the 4th. And then anything that's still underneath that radical gets put back together as well, and all we happen to have left is just a y. So there we are. This was a rather long lesson. We had a lot to learn and a lot to cover. If you have any questions, please let me know. I will be more than happy to answer them and cover anything with you. Thank you for your patience, and thank you for watching this lesson.